In this video, we're going to go through classifying acids and bases. We'll answer the essential question, how can we identify acids and bases, and what determines their strength in chemical reactions? So we're going to look at two definitions of acids and bases, and we're going to start with the Arrhenius definition. So in this definition, acids donate hydrogen ions in water, and bases donate hydroxide ions in water. Now, a limitation of this definition is it will only work for substances that contain hydrogen or hydroxide, and NH3, for example, is a base that doesn't contain hydroxide, so this definition will not always work. Now, the Brønsted-Lowry definition is going to be the main theory that we're going to use. In this definition, acids donate a hydrogen ion, and a base accepts a hydrogen ion. Okay, so we're going to look at an example in a second where you'll see acids are going to donate hydrogens and bases are going to accept hydrogens. Now, when we have this pair where one is donating a hydrogen ion and one is accepting, we call these conjugates. So these are pairs of substances that are going to differ by one hydrogen ion. So here's an example. It says identify the acid base, conjugate acid, and conjugate base. All right, so we have one species on the left-hand side that contains nitrogen and one species on the right-hand side that contains nitrogen. If you notice, the difference between the species on the left and the right is a hydrogen. So to go from here to here, I would have to lose a hydrogen. So the species on the left is going to be our acid because it is losing a hydrogen. And then on the right-hand side, this is going to be our conjugate base. If I go the other way, notice, I go from not having a hydrogen to a hydrogen, and we know that bases pick up hydrogens. So that's why it's considered a conjugate. All right, let's look at our other pair. So here we have H2O, and then we have H3O. So to go from having two hydrogens to having three hydrogens, we would have to pick up a hydrogen. So that would make this our base, and this would be our conjugate acid. And again, going in reverse, I go from having 3 to 2, which is by definition an acid. So every acid will have a conjugate base, every base will have a conjugate acid. Now, in a solution, if you generate or if you put out H3O+, that will make it an acidic solution. If OH is a product, it will be a basic solution. So here are three examples. In the first example, we're kicking out H3O+, that makes this an acid. In our second example, we're kicking out OH-, that would make that a base. Now, look at the third example. We're kicking out an OH, so that would make it a base. All right, we have a couple types of acids. We have monoprotic, which donate one hydrogen ion. We have diprotic, which donates two hydrogen ions. And then we have polyprotic, which donates more than two hydrogen ions. We also have what's called amphiprotic or amphoteric substances, which can act as either an acid or a base, and water would be an example. Water can be an acid by donating a hydrogen, or it can pick up a hydrogen and act as a base. Okay, now strong acids and bases fully dissociate in water, so they will completely break down into their different pieces. They're going to have large K values. Weak acids and bases only partially dissociate in water, and they're going to have small K values. Now, just a couple important things. Strength of an acid or a base does not have anything to do with concentration. Okay? Strong acids are going to have a weak conjugate base. Strong bases are going to have a weak conjugate acid. Okay, now we've talked about equilibrium already, but acids and bases have their own K values, and these K values tell us how well it's going to dissociate. So again, if you have a strong acid or base, you're going to have a large K value because it is going to fully dissociate in water. Weak acids and bases are going to have a small K value because it will not completely dissociate in water. Now here, this is the general format for, let's try to pick a color you can see. This is the general format for an acid dissociating. So you'll have, it'll be comprised of a hydrogen and a conjugate base, which is going to be our A. You've got water in solution, so it's going to dissociate. You'll end up with H3O plus and A, which is going to be our conjugate base. So we express Ka, it's going to be the ratio of the pieces that dissociate. So this is essentially the left side, or the product side of our reaction, over the reactant side. And we're just looking at HA. We're not looking at our water here. When we write out our expression for Ka, we are going to exclude liquids and solids, only things that are aqueous. Most acids are weak, meaning that they'll have a low Ka value, so less than 1. Kb is our base dissociation constant, and again, here is our general format for a base dissociating. On the right-hand side, we have hydroxide and Hb, and if you look at our Kb expression, that is going to be in our numerator, and then on the left-hand side, we have our reactants, and those are going to be our base, which will be the denominator of our expression. And remember, strong bases are going to fully dissociate in water. They're going to have large K values. And weak bases will only partially dissociate in water and will have small K values. And that's it. That's how you classify acids and bases.